Hello viewers, welcome. Now we have this question that says obtain the dimensional formula of the following physical quantities: universal gravitational constant, the coefficient of viscosity, specific heat, and Planck's constant. Now before we go ahead and solve this question, if you are watching us on Facebook, please follow our page. If you are on YouTube, subscribe to the channel, like and comment. Don't forget to turn on the bell so that you can be notified every time we post. Now let's look at the first one, which is the universal gravitational constant, G. Now, from Newton's law of gravitation, the force is given by G multiplied by M1, that is multiplying by M2, and this is divided by R squared, where the F is force, G is the universal gravitational constant, M1 and M2 are masses, and G, R is radius. So what we are looking for here are the dimensions of this G that we have here. So the first step we'll take is make G the subject of the formula. So let's quickly do that. This is like over 1, so we cross multiply. When we do that, we're going to have G M1, M2 will be equal to F multiplied by R squared. Since we're making G the subject, we're going to divide by M1, M2. Here we're also doing the same on the other side. We have M1, M2 there. So the M1, M2 on this side will cancel. This will go with that. And what we're going to have is our G will now be equal to the force multiplied by R squared. That will be divided by M1 and M2. Well, so there we have it. We have made G the subject of the formula. Now that we have made G the subject of the formula, it will be easy for us to find its dimensions. So the first step again we need to take here is look for dimensions for each of the physical quantities that we have here. We have force, we have R, which is radius, and we have the masses. So let's look at the dimensions for each of those. Let's start with force. Now, force from Newton's second law of motion is given by ma. Force is equal to ma, where the m we have here is mass and a is acceleration. The units for mass are kgs, and the units for acceleration are meters per second squared, or per square second. Now we can write this one in this format where we are saying kg multiplied by m, that is multiplying by s to minus 2. Remember, when we have 1 divided by x like this is the same as x to the power of minus 1. So this in this law is the same that we are applying here, where we are saying we have m divided by s to the power of 2. When s goes on top there, the power will become a negative. So that's why we have a minus 2 here. So now that we have the units, we can basically find the dimensions for force, and we'll say the dimensions for force will be equal to the dimension for kg is capital M, which is mass. Then m is meters, which is basically just length. So have L there, and s to the minus 2 seconds, this is time, and its dimension is capital T. And this must be given to the power of minus 2. So these are the dimensions of force. All right. Now that we've found for force, let's also look at the dimensions for r squared. Now, r is radius. Radius is basically just length. So radius is measured in meters. Those are the units. And the dimension for r is just equal to meters. That's length. So we have L there. And then since what we have there is r squared, the dimension for r squared would be just L to the power of 2 as well. So these are the dimensions, or this is the dimension for r squared. And then the M1 and M2 are basically masses. So masses, which is M1 and M2, they're basically measured in kgs. And the dimension for kg is capital M. So this is what we have as dimensions for this. So this is the dimension for the mass. This is for the radius, which is r squared. The dimension for r is L, but since it's squared, we have L squared. For force, we have those three there, M, L, T to minus 2. So now that we've found the dimensions on that side, all we have to do is just replace. So we'll say the dimensions for G now on this side, G, let me just write that one properly. G will be equal to, we replace on top there, we have the dimensions of M, L, T to minus 2. Now we need to show that we are looking at dimensions. So the square brackets here are telling us the dimensions of G are equal to, then for R squared, we have L to the power of 2. Then down here, what we have is M1 and M2. So it's just M that is multiplying by another M. So these are capital letter M's for the dimension. Now let me get rid of this other part here so that we can have. All right. So we continue now. What we have here is M LT minus 2. Then we also have L to the power of 2 on the other side. So L is common. When we write like terms together here, we'll say this can be separated in this format for you to understand very well. This is equal to, we have M, see the dimension, that is multiplying by L. I'm just separating what is inside brackets here. Then we have T, the T is to minus 2. So T to minus 2 like this. Then this is multiplied by also L to the power of 2 for us to understand very well. Then we have M and M down there. Now, what is happening on top there is we're going to bring like terms together, and what we say is this will be equal to the L multiplied by that L squared on the other side there. What we're going to have is M multiplied by T to minus 2 multiplied by L, that is multiplying by L squared. Now, L multiplied by L squared, this will give us L to the power of 3. Okay, we have L, which is to the power of 1 in short, then it is multiplied by L to the power of 2. So when you have the same variables, all you have to do is add the powers. So when you add 1 plus 2, this will give us 3. So this is what we have top there. Then down here, M multiplied by M will just give us M to the power of 2. Now that we have this, it implies to say it will be easier for us to cancel out. So this M that we have on top here, the m will go once there, leaving a 1. The m will go once here, leaving m. That implies to say what we are going to have here is the dimensions for G will be equal to, on top there, we're going to have T to minus 2, then L to the power of 3. So that's what we have on top. And then down here, we'll just have M. So T to minus 2, L to the power of 3 divided by M. So this will conclude in this manner. Taking the M on top there, what we are going to have is, when you take the M on top, remember M, the way it is here, it is to the power of 1. But since the power is 1, we don't need to show it. So when you take it on top, it means the 1 will come in. Taking this on top, we'll have G. Dimensions for G will be equal to M. When we take M, the power becomes negative, so minus 1. Then L to the power of 3. Then T to the power of minus 2. So these are the dimensions for G, which is the universal gravitational constant. So we have it there. Now let's look at the coefficient of viscosity. From the formula that says force is equal to the coefficient of viscosity multiplied by A, that is multiplying by dV dx. If we make the coefficient of viscosity the subject here, what we are going to have is the coefficient of viscosity will be equal to the force divided by area, that is multiplying by dV dx, like that. So this will be the formula that we are going to have there for the coefficient of viscosity. Now, the next step we need to do again is just find the dimensions for each of these physical quantities that we have here. So let's do that. Starting with force, by now we understand, say, force is given by MA, and this is still kgs, that will multiply by meters, that will multiply by s to minus 2, and this will give us the dimensions of mass multiplied by length, that is multiplied by t to minus 2. So these are the dimensions for force. And then the area is measured in square meters. So the dimension for area, the units are square meters. So meters is length, and we'll have L squared for area. So this is the dimension we have for area. For V, dV on top there is just change in velocity. So we are dealing with velocity. Velocity is measured in meters per second. This is the same as meters multiplied by s to minus 1. And this will have the dimensions of L, that is multiplying by t to minus 1. So these are the dimensions for velocity. X is just distance. So distance is measured in meters, and this will have a dimension of just L. So those are the dimensions we're going to have for each of those. X is L, V is LT minus 1, then we have L squared for area, and we have that for force. Now let's replace with what we have. So the dimensions for the coefficient of viscosity will be equal to, for force we have M LT to minus 2 on top there. Then this will divide by area, which is L squared, that will multiply by, we'll have L T to minus 1, that is dividing by X is just L here. So this is what we have when you replace. So let's continue with our calculations. So here we can see down here we are going to have this L and that L cancel since they are the same. So when we do that, what we are going to have is the coefficient of viscosity dimensions will be equal to M. We'll have L, we'll have T to minus 2. Then this will divide by what remains down there is L squared multiplied by T to minus 1. Again, when we reach this stage, we can see we still have like terms. We have T to minus 1 and T to minus 2. We have L on top and L squared down here. So let's see what cancels. So L will go once there, leaving a 1. It will go once here, leaving L. And then for T minus 2 and T minus 1 down here, when you have the same bases that have got powers, for example, these are the same variables. We have T on top, T down here. They are dividing. So all you have to do is subtract the powers. So what we have here is, we'll have minus 2 subtracted by minus 1, and this will just give us minus 2 plus 1, which is giving us minus 1. So we'll still have T as a base, but with the power of minus 1. So yeah, let's do that. So what will remain here is, we'll say we have M on top there, then our T will be to minus 1, then we'll have our L remaining down here. So this to be written in the standard form, we need to make sure we write L before T, and this will be equal to M, then we'll have T minus 1, then we'll have L. I've written T before L again. Let me rewrite that one. So we'll have L to minus 1 and we'll have T minus 1. So these are the dimensions we're looking for the coefficient of viscosity. What has happened here, if I was to take you through the process, at this stage here, maybe this stage might be confusing on how we came up with T to minus 1 and L to minus 1. So let's go back there and say we cancelled L on top and L squared down here, leaving L. So what we are going to have now is, we'll have this is equal to, on top there we'll have M. The L is cancelled, so we only have M minus 2. Then down here we have L and we still have T to minus 1. When you reach this stage now, the common variable that we have is basically T. So now this is where this process comes in. After we subtracted, we found that our power will be minus 1. So this will be equal to, now we'll have our M. Then when we take this L on top, since it's down, it's going to have a negative power. So that's a minus 1. And then our T is also having a minus 1. So that's how we came up with the dimensions like that from this stage here. I hope it's understood now. We'll go to the next one. So let me get rid of this. All right, so the next one is specific heat capacity. Now, specific heat capacity is given by, from the formula where we are saying heat energy is equal to mass multiplied by the specific heat capacity multiplied by change in temperature, which is change in heat. The C is the specific heat capacity we're talking about. So we'll make it the subject. When we do that, we'll say our C is equal to Q divided by M, that is multiplying by change in temperature. Our C will be equal to Q divided by M, that is multiplying by T. Now change in temperature is just temperature, so we'll leave it as a T like that. Where this Q that we are seeing up here is heat, so heat is a form of energy, so it's measured in joules, and we have the M, which is mass, and we have T, which is temperature. So again, as usual, we are going to establish the dimensions for each of these. Let's look at the dimensions for energy, which is heat energy in this case. Now, getting it from the formula, we can get it from anywhere. We can get it from the kinetic energy formula. You know, kinetic energy is energy. We can get it from the potential energy formula. We can also get it from the work formula. So I'll use the simplest one, which is let's get potential energy. So potential energy is equal to mgh, where m is mass, g is acceleration due to gravity, h is height. So mass is measured in kgs, acceleration is measured in meters per square second, and the height is measured in meters. This is giving us kgs. M multiplied by m will give us m squared, and then s minus 2. So bringing in the dimensions now, what we have is kg is m, that's L, and is squared. Is squared, then we have s, which is given to minus 2, and that's not s, but t now is a dimension, so we'll have t minus 2 like that. So these are the dimensions we have for energy. Those are the dimensions we have for energy. M, L to the power of 2, then T to minus 2. All right, so let's look at the other part, which is M. M is mass, and mass is measured in kgs, and the dimension here for kg is just capital M like that. So we have it there. Then temperature. Temperature is measured in kelvins, and its dimension is just K. So that's what we have there. Now that we have established the dimensions for each of the quantities we have, it means we are now good to replace and then come up with the dimensions for the specific heat capacity. So let's go ahead and do that. C will be equal to, on top there, the dimensions we have are M. Just put this like that. Yes, M. We have L to the power of 2, then T to minus 2. And this will divide by, for mass, we have M. Then for temperature, we have Kelvin like that down here. Yeah, so this like multiplying like that. When you look at what we have here, we have something that is common. This M on top will cancel with the M we have down here. And what we'll have now is this will be equal to, we'll have our L to the power of 2, T to minus 2, and then we'll have our K down here. Yes, so when we take our K up, what we'll have is L to the power of 2, T to the power of minus 2, and K to the power of minus 1. So these are the dimensions that we are looking for specific heat. So there we have it. All right, so we're on Planck's constant. Now, Planck's constant, getting it from the formula, which says E is equal to hv, where h is Planck's constant, v is frequency, and E is energy. Making h the subject of the formula, we'll have it as energy divided by frequency. Establishing the units for energy again, as we did earlier on. Now we're going to use a different one. So we'll say we have energy, dimensions for energy, getting it from the kinetic energy formula that says is half mv squared. We find that half is a constant, we don't consider it here. So what we have is mv squared, where m is mass and v is velocity. Mass is measured in kgs. Velocity is measured in meters per second, but this is squared. So what we have here is kgs m squared, that is divided by s squared. When we take our s squared on top there, what we are going to have is this. So kg m squared s to minus 2. And this will give us the dimensions of m, l, the power of 2, and t to minus 2, which are the dimensions of energy that we basically established even on the other side. Then V is frequency. Frequency is measured in the units of hertz, and this is the same as 1 over s, which is per second, and it can be represented by s to minus 1. S is time, so the dimension will be t to minus 1. So this is the dimension that we're going to use for frequency. Now let's replace. Replacing, what we are going to have is the dimension for h will be equal to, on top there, we have m, we have l to the power of 2, we have t to minus 2, and this will be divided by t to minus 1, like that, down there. So this will proceed to be, we'll have m l to the power of 2. As we did earlier on, t and t are dividing, so we're going to subtract their powers. So we'll have minus 2 minus minus 1, which will just give us minus 1. This will be minus 2 plus 1, which is minus 1. This implies to say we're going to have our t to the power of minus 1. And these are the dimensions we are looking for in Planck's constant. Yes. So here we have it. Thank you for watching. Don't forget to follow us